Okay, so section A, you see, look at this section. So let's be on the same page. So this section A, you're looking right. Okay, so the section marker shows direction in which you're looking. You look right. So if you go to section A, you see where you're looking right is showing that the roof is sloping down as well too, you know. And then this is also sloping this way. So we talked about the roof structure, you know, this is sloping down and this other side is sloping in that direction. This section B we're looking at. So this is a brief description of the architecture. You know, so once you get an architectural design like this, the first thing you would need to do is to study the architectural design. The responsibility of a structural engineer is to frame the building, provide his structural framing arrangement of all the structural entities that will support the entire structure. These structural entities, which is the skeleton of the structure, comprises of the structural beams, the structural columns, the structural slab, the structural foundation, and the structural access stair. Okay, the structural beams, the structural slab, the columns, the access stair, and the foundation structure. It is the structural engineer's responsibility to completely design the entire structure so that it can withstand the loads that it will take or it will be subjected to during its service life. So how do we go about these very important onerous tasks? Let's look at that together. Now, when we received this structural drawing, we studied the structure, we obtained the subsurface investigation reports, otherwise known as the geotechnical investigation report. The geotechnical investigation report will give you information on the subsurface characteristics of the site. It will reveal information of the soil stratigraphy, the vertical sequence of stratified soil, the lateral extent, and the nature and location of the groundwater table. The report will contain certain in situ tests and laboratory test results to classify and obtain the index properties of the soil. Index properties of an in situ soil are properties that are indicative of the engineering characteristics of the soil. As a structural engineer or as a civil engineer, you need to establish the engineering properties of the soil and to be able to classify the nature of soil present on site so as to be able to calculate the ultimate bearing capacity of the soil, because your structure is going to be sending forces down to the bearing stratum. So you would need to study the subsurface investigation reports, typical tests that are carried out on site, a trial pit, the Dutch cone penetration test, the standard penetration tests together with borehole logging. The Dutch cone penetration test is a continuous testing approach where a standard penetrometer is sent down with a rig. The penetrometer is driven at 2 centimeters per second, and then it records from the cone tip, it records the penetration resistance of the soil stratum. In addition, there are certain sensors that are placed on the cone tip that will be able to measure real time the pore pressure, the dynamic or hydrostatic pore pressure beneath the soil stratum. The cone penetration test can also give you, with empirical expressions, the undrained shear strength of the soil. You can also use that to determine, with Meyerhof expression, the ultimate bearing capacity of the soil, okay, via empirical expressions. Another form of in situ testing that is done on site is what we refer to as the standard penetration test. Standard penetration tests are usually carried out on granular soil materials. You don't carry out standard penetration tests on cohesive soils, okay, because these are plastic soils with most likely collapsible properties. So standard penetration tests are carried out on cohesionless soils, granular soils such as sand, medium dense sands. You drive a standard hammer. It's used to drive down a split sampler. The number of blows that is used to drive it down for 6 inches is not recorded, but the number of blows that is used to drive it further down by 12 inches is recorded as the blow count. That is standard penetration test. So the penetration test and this test you carry out on site is used to obtain crucial shear strength properties as to classify the type of soil that is present on site based on one of the classification systems, either the ASHO classification system, the A category classification system, or the unified soil classification system. This will give us very important information on the gravimetric and shear strength properties of the soil, as well as the plastic properties of the soil and the ability of the soil to undergo plastic deformation. From what we saw on this site, from the geotechnical investigation report, it was clear that the soil was the site terrain is filled with, underlain by very thick layer of peat. The site was originally a dump site and was filled with dump materials. Particle sizes less than 0.002, indicative of organic clay, was present on site, up to 20 meters. The site was so poor, and this is the reason why the architect decided, in compliance with us, the structural engineers, to elevate the entire structure so that the entire structure will be sitting on very deep pile foundation. We wouldn't go into the pile foundation structural analysis because that was done based on a non-linear pile soil spring idealization. But at this point, we want to focus on the structural design of the superstructure, and we want to take you through how that is done with staad. So we studied the architectural drawing. So when you look at this architectural drawing, one of the issues we had, let's look at this entire thing. This is a live project, so we'll be taking you through all the concerns that we went through and how it was resolved. Now, the first thing we try to do is, okay, so let's look at this carefully. Now, this is the architect's proposal. This is the, like we said, this is the ground floor structural architectural layout, sorry. There's the access here, there's an access on that side, on the rear, and then there's an access on the right, access there on the left as well too. Now, the man has proposed columns to be on these locations. Now let's see what happens when we try to superimpose these on our proposed structural layouts. Okay, now if you look at what we did here, the red indicator, or the red filled column, shows the position in which the architects had placed his columns. Okay, so what you have here actually indicates, the red and blue indicates the positions in which the architect has indicated where the columns will be. Now, when we tried doing a preliminary structural framing, so what you can see here is a preliminary structural framing. Okay, so this is the first to third floor plan. Now, the line you see here, okay, is the boundary of the first floor architectural layout. Let's look at it very carefully. Okay, so this is the first to third floor plan. Now, if you look at this, this is the ground floor. The green indicator you see here by the architects is the boundary of the ground floor plan. Now look at, that's grade 4 and that's grade 1. So if you come here, you see grade 1 and then grade 4, and then we have grade A and then grade L. So grade A and grade L. So that's the boundary of the ground floor plan. Okay, so if you decide to move, let's try something. Okay, let's look at the concerns we had. Firstly, you try with the architect's proposal, right? Now, if you move these columns with a common grid point and you position them here, now what you will see, so we are trying to do this preliminary structural framing. You would see that these columns will puncture into the slab on the first floor. Okay, and if you allow this go to the roof the way it is, it means that it's going to puncture all through the slabs from the ground, from the first floor up onto the roof level. Okay, so the columns at the edge, this column, this would not be exposed because you have a wall there. Okay, so it's going to be hidden in this wall. This will be exposed, it will not be hidden. This will be hidden, but this column would not be hidden. This will puncture through the slab fully. This column would be hidden. This would be this would be, and so on. So based on this, what we decided to do was to flag up some of these columns so you could see the position in which the architect has originally presumed the columns would be. However, when you develop your structural framing arrangement, okay, your preliminary structural framing arrangement to carry the superstructure, you may find out that the column positions may either be uneconomical or may interface with the original aesthetic of the structure. In our own instance, we saw, look,